Welcome back to the deep dive. Last time, we took a kind of bird's eye view of computer architecture, really getting those foundational concepts down, how these amazing machines are built, how they think. Today, we're diving deeper. We're zooming right in on what's essentially the beating heart of it all, the central processing unit, the CPU. It really is the brain of the system, and frankly, it's a marvel of engineering. To help us navigate its, intricate landscape, we're really thrilled to have our expert back with us.
Hello, everyone. Thank you for having me. It's a great pleasure to be here to discuss this important topic.
Oh, the pleasure is absolutely ours. So our mission today, for you listening, is to give you a really solid, comprehensive understanding of the CPU. We're going to dissect its key components, try to demystify how it actually operates, break down performance metrics, what makes one faster than another, and even touch on the big design philosophies behind it all. So whether you're deep into computer science studies or just, really curious about what makes your phone or laptop tick, we're aiming to pull out the most crucial insights. The goal is to help you become genuinely well-informed. All right, let's jump right in. The CPU. It seems incredibly complex, but I understand it can be broken down into three main functional units. What are they, and what do they do together?
Yeah, that's a great place to start. It's helpful to think of the CPU as this highly coordinated internal team. Right at its core, it revolves around what we sometimes call the triumvirate of processing. These three primary units are the Arithmetic Logic Unit, or ALU, the Control Unit, the CU, and the registers. Together, these three work in, a tight, incredibly high-speed concert. They're constantly interacting, doing all the calculation work, directing the flow of data, and executing program instructions at really astonishing speeds.
A triumvirate. I like that. It paints a picture of collaboration. Okay, so if the ALU is one of those key players, could you elaborate on its role? You mentioned it has a dual role. What exactly does that entail?
Absolutely. The ALU is essentially the CPU's computational engine. It's where the raw calculations happen. Its dual role covers two main types of operations. First, you've got arithmetic operations. This is your basic math, integer addition, subtraction, multiplication, division, things like that. And crucially, modern ALUs almost always include a dedicated floating point unit, or FPU. This is specialized hardware just for calculations involving non-integer numbers, decimals, basically. These are absolutely vital for things like scientific computing, physics simulations, or rendering all those complex 3D graphics in video games. Then the second part of its role is logical operations. These are your Boolean operations, N, 1 or not, XOR. Think of them as true-false comparisons or logic tests. They are absolutely fundamental for any kind of decision-making within a program. Like a program might use an A&D operation to check if, say, two different conditions are both true before it does something, or maybe an OR operation to see if at least one condition is met. The ALU handles all of that fundamental logic.
Okay, so the ALU is the number cruncher and the logic tester. Got it. But like you said, a brain needs coordination, not just calculation. That brings us to the control unit, the CU. How does it fit in? And what makes its job so different from the ALUs?
Right, that's a really critical distinction. If the ALU calculates, the control unit orchestrates. It's the director, the manager. It actually performs no calculations itself, zero. Its job is pure management and coordination. The CU directs the flow of data between the CPU's own components, like getting data to the ALU or into registers, and also manages the traffic between the CPU and other parts of the computer system. Think main memory, input-output devices, graphics card, etc. Its absolute core responsibility, though, is managing the instruction cycle. This is really the heartbeat of the CPU's operation. The CU fetches instructions from memory, it interprets them, we call this decoding, and then it generates very precise, timed control signals. These signals tell the ALU, the registers, and other components exactly what to do, step by step, and critically, when to do it. It's the traffic cop, the conductor, all rolled into one.
The nerve set. Yeah, that makes a lot of sense. Okay, orchestrator, not calculator. Now, the third part of that triumvirate, registers. What exactly are registers? And could you maybe focus on two really fundamental ones, the program counter and the instruction register?
Registers are fascinating and absolutely vital for speed. They are small, extremely fast, temporary storage locations, physically located directly on the CPU chip itself, on the silicon die. You can imagine them as the CPU's immediate workbench or maybe a scratch pad. Because they're right there, accessing data in a register is incredibly fast, orders of magnitude faster than going out to the main system memory, the RAM. This proximity is crucial for keeping the CPU running at full tilt. Now, there are various types, but let's look at those two key ones. The program counter, or PC, is a special register. Its job is to hold the memory, address the location of the very next instruction that the control unit needs to fetch from memory to execute. As soon as an instruction is fetched, the PC automatically increments, like turning a page, to point to the instruction right after it. This keeps the program flowing sequentially unless told otherwise. The instruction register, or IR, is where that instruction, once it's fetched from memory, gets stored temporarily. The control unit's decoder circuitry then looks at the binary pattern sitting in the IR to figure out exactly what the instruction is telling the CPU to do. So basically, the PC says where to get the next instruction, and the IR holds that instruction while it's being decoded and prepared for execution.
Okay, super fast scratch pads right on the chip. Makes perfect sense for speed. Now, we mentioned interacting with main memory, which is obviously much slower. How does the CPU actually talk to the main system RAM? Which specific registers are involved in that communication?
Right, that interaction is fundamental, and yeah, it involves managing that speed difference. Two specific registers are key facilitators for talking to main memory: the memory address register, MAR, and the memory data register, MDR. When the CPU needs to read data from memory or write data to it, it first puts the specific target memory address, the location it wants to access, into the MER. This address is then sent out on the system's address bus, essentially telling the main memory controller which specific location to interact with. Now, if the CPU is performing a write operation, the actual data it wants to write is placed into the MDR. This data travels across the data bus to the memory location specified by the MER. Conversely, if it's a read operation, after the memory controller finds the location using the MER, the data retrieved from that memory address is sent back across the data bus and placed into the MDR. From there, the CPU can move it into another register or the ALU for processing. So MER points the way, MDR holds the goods, basically.
And MAR points, MDR carries. Got it. Okay, we got the team ALU, CU registers and how they talk to memory. But the real work, the fundamental rhythm, is that instruction cycle you mentioned. You called it the heartbeat. Let's walk through that. Starting at the beginning, the fetch stage, what's happening there?
Exactly. The instruction cycle, often called the fetch, decode, execute cycle, sometimes with a write-back stage, this cycle is the fundamental operation. It repeats constantly, millions or even billions of times every second. The first stage is fetch. This is where the control unit initiates the process of getting the next instruction. It looks at the program counter, PC, remember? The PC holds the address of the next instruction. The CU takes that address from the PC and places it onto the address bus, signaling the memory controller. The memory system finds that location, retrieves the instruction stored there, and sends it back across the data bus to the CPU. This incoming instruction is then loaded into the instruction register, IR. And crucially, almost simultaneously, the program counter, PC, is incremented to point to the address of the following instruction in the sequence. This ensures that the CPU is immediately ready to fetch the next instruction as soon as the current one moves along the pipeline. No time wasted.
Fetched, and the PC is updated. Ready for the next one. Okay, so the instruction is now sitting in the instruction register. What happens next? What occurs during the decode stage?
Right, so the instruction is now in the IR. The decode stage begins immediately. This is where the control unit's specialized instruction decoder circuitry gets involved. It examines the binary pattern, the ones and zeros of the instruction held in the IR. It breaks this instruction down into its core parts. Typically, an instruction has two main pieces: the opcode, operation code, which specifies the actual action to be performed, like add, subtract, load data, store data, jump to a different instruction. And the operands, which specify the data or the memory locations or the registers that the operation should use. Based on interpreting the opcode, the decoder generates a series of internal control signals. These signals are tailored precisely for that specific instruction and are sent out to activate the necessary parts of the CPU, like the ALU, specific registers, or the memory access units preparing them for the next stage. Execute.
Decoding figures out what to do and who needs to do it. Okay, we've fetched it, we've decoded it. Now for the payoff, right, where the actual action happens, the execute stage. And you mentioned sometimes the store stage. Tell us about those.
Exactly. Now comes the execute stage. The control unit, having decoded the instruction, now issues those specific control signals it generated. These signals activate the appropriate functional units to actually carry out the command. What happens depends entirely on the instruction. If it's an arithmetic or logical instruction, the CU directs the ALU to perform the specified operation, like addition or an AND comparison, on data that's typically already been placed in general purpose registers. If it's a data transfer instruction, like load or store, the CU manages the movement of data. This could be between a register and a memory location, using the MAR and MDR we discussed, or maybe just between two different registers. And importantly, if it's a control flow instruction, things like jump or branch, the CU doesn't necessarily involve the ALU. Instead, it might directly modify the program counter, PC, loading it with a new address. This is how programs make decisions or loop. And if statement that's true might cause a jump to a different part of the code, skipping the next sequential instruction, this changes the flow of execution. Then, following the execution, there's often an optional final stage. Store, sometimes called writeback. If the execution stage produced a result, like the sum from an addition, this stage writes that result back. It might go into a specific general-purpose register for quick access later, or it might be written back out to main memory via the MDR. And this whole cycle, fetch, decode, execute, maybe store, is driven relentlessly by the CPU's internal clock. We're talking billions of cycles per second in modern processors. It happens incredibly fast.
Incredible speed. That's the perfect segue. We always hear about performance, clock speed, cores, threads, especially when comparing CPUs. How do these key metrics actually relate to each other? What makes one CPU faster than another?
Yeah, understanding performance is definitely more nuanced than just looking at one number. Let's break those down. Clock speed is probably the most famous metric. It's measured in gigahertz, GHz, which means billions of cycles per second. So a 4.0 gigahertz CPU has an internal clock that ticks 4 billion times every second. This clock synchronizes all the operations within the TPU, like the stages of the instruction cycle. For a long time, faster clock speed was the main goal, like a faster assembly line, but it's definitely not the whole story anymore. Then you have cores. Modern CPUs are almost all multi-core. This means a single physical CPU chip actually contains multiple independent processing units. Each core typically has its own ALU, its own control unit, its own L1 and often L2 cache, and registers. Think of it like having multiple brains in one head. Each core can execute its own completely separate stream of instructions at the same time as the other cores. This allows for true parallel processing or multitasking, running multiple complex applications smoothly. That's largely thanks to multiple cores. And finally, threads, or more accurately, hardware threads. This often refers to technologies like Intel's hyperthreading, which is a form of simultaneous multi-threading, SMT. What this does is allow a single physical core to handle two or sometimes more streams of instructions, called threads, concurrently. It makes one physical core appear as two logical or virtual cores to the operating system. The core duplicates some of its internal resources, so if one thread gets stalled, maybe waiting for data from slow RAM, the core can switch to working on the second thread almost instantly, keeping the execution units busy. It improves efficiency and throughput, but, it's generally not as effective as having two completely separate physical cores. It's more like one worker juggling two tasks very efficiently.
Okay, so clock speed is the pace. Cores are like multiple workers, and threads help one worker juggle better. That clarifies things. But there's another term that seems crucial for efficiency: instructions per cycle, or IPC. Why is IPC so important when we evaluate CPU performance?
IPC is absolutely crucial, yes. It gets to the heart of a CPU's architectural efficiency. IPC measures, on average, how many instructions a single CPU core can actually complete or retire in one clock cycle. Think of it this way. Clock speed tells you how many cycles happen per second, but IPC tells you how much work gets done in each of those cycles. A CPU with a more advanced internal design, maybe better branch prediction, a smarter pipeline, more execution units will have a higher IPC. This is exactly why, say, a modern 3.5 GHz CPU can absolutely demolish an older 4.0 GHz CPU in performance benchmarks. The newer chip, despite a technically slower clock speed, might have a significantly higher IPC. It's just getting more useful work done with each tick of that clock. So ultimately, you have to consider all three. Overall CPU performance is really a product of clock speed multiplied by the number of cores multiplied by the instructions per cycle, IPC. That combination gives you a much better picture of its true computational power.
That formula really puts it into perspective. Clock speed X, cores X, IPC. Excellent. Now let's circle back to a challenge we touched on in our foundational concepts discussion: that inherent speed difference between the superfast CPU and the, comparatively sluggish main memory. The von Neumann bottleneck. What's the main way designers tackle this, and what principle makes it work?
Ah yes, the von Neumann bottleneck. It's a persistent challenge. The CPU is often starved for data because the main memory just can't keep up. The primary and most effective solution employed in virtually all modern processors is CPU cache. Cache is essentially a small amount of very, very fast but also expensive memory. It's typically static RAM, or SRAM, which is much faster than the dynamic RAM, DRAM, used for main memory. And critically, this cache memory is built directly onto the CPU die itself, or sometimes very close by in the CPU package. It acts as a buffer, a staging area holding copies of data and instructions that have been recently used or that the CPU anticipates needing soon. Now, why this works so well relies on a fundamental principle of computing behavior called the principle of locality of reference. This principle has two main aspects. Temporal locality. If a program accesses a piece of data or instruction, it's very likely to access that same piece of data or instruction again soon. And spatial locality. If a program accesses a particular memory location, it's very likely to access other nearby memory locations soon after, like the next elements in an array or the next instructions in a sequence. Because programs exhibit this locality, there's a very high probability, often over 90%, that the next piece of data or instruction the CPU needs will already be present in the cache. This is called a cache hit. When a hit occurs, the CPU gets what it needs almost instantly, avoiding that slow round trip to main RAM. Cache misses, of course, still happen, forcing a fetch from RAM, but the high hit rate dramatically boosts average memory access speed and overall performance.
Locality of reference. Makes sense. Programs tend to reuse things or work on things that are close together, so the cache is like a super fast buffer. But I understand it's not just one monolithic block of cache, right? Can you describe the typical structure? This multi-level cache hierarchy.
That's right, it's not just one big cache. To optimize the trade-offs between speed, size, and cost, modern CPUs use a multi-level cache hierarchy. Typically, you'll find 3 levels, labeled L1, L2, and L3. At the very top, closest to the actual processing units of each core, is the L1 cache. This is the smallest cache, usually measured in kilobytes, like 32 KB or 64 KB per core, but it is by far the fastest, offering near register access speeds. L1 is often split into 2 parts, an L1 data cache, L1D for data, and an L1 instruction cache, L1I for instructions, allowing simultaneous access. Next down is the L2 cache. This is larger than L1, maybe hundreds of kilobytes or even a megabyte or 2 per core, and slightly slower, but still extremely fast compared to RAM. In most modern designs, each core has its own dedicated L2 cache. If the data isn't found in L1, the CPU checks L2 next. Finally, there's the L3 cache. This is the largest level, often measured in megabytes, ranging from maybe 8 megabyte up to 64 megabyte or even more in high-end CPUs, and it's the slowest of the 3 cache levels. However, it's still significantly faster than accessing main system RAM. A key characteristic of L3 cache is that it's typically shared among all the cores on the CPU chip. It acts as a larger common pool of frequently used data, serving as the sort of last stop cache before the CPU has to go out to the main memory. This hierarchical structure works because most memory accesses hit the tiny, ultra-fast L1. Fewer accesses miss L1 but hit the larger, slightly slower L2. Even fewer miss both L1 and L2 but hit the large shared L3. Only the remaining small fraction of accesses need to go all the way out to the much slower main RAM. It's a very effective system for bridging that speed gap.
A tiered approach, fastest and smallest closest, largest and slowest further away, but all faster than RAM. Brilliant. Okay, let's shift gears slightly to the CPU's fundamental language, how to actually understand software commands. This involves the instruction set architecture, or ISA. I hear there are 2 dominant design philosophies here, CISC and RISC. How do they differ?
Yes, the ISA is absolutely fundamental. It's the contract, the vocabulary, the interface between the hardware, the CPU, and the software program's operating system's compilers. It defines the set of basic operations the CPU knows how to perform. And you're right, historically and currently, there are 2 major design philosophies, CISC and RISC. CISC stands for Complex Instruction Set Computer. This was the dominant philosophy in the early days of microprocessors and is still used in the ubiquitous x86-64 architecture found in most desktops and laptops from Intel and AMD. The CISC approach aims to make the hardware powerful by including instructions that can perform complex, multi-step operations in a single command. For example, a single CISC instruction might load a value from memory, add it to a value in a register, and store the result back to memory all in one go. The idea was partly to make the job of assembly language programmers and early compiler writers easier, as they could use these powerful single instructions. However, this leads to more complex CPU hardware needed to decode and execute these varied and intricate instructions, which can consume more power in silicon area. Then, starting around the 1980s, the RISC philosophy emerged, Reduced Instruction Set Computer. The core idea behind RISC is to simplify the hardware by using a much smaller, highly optimized set of very simple instructions. Each instruction does only one basic thing, like load from memory into a register, ADD2 registers, store a register's value back to memory. These simple instructions are designed to be executed very quickly, ideally within a single clock cycle, and in a predictable way using a technique called pipelining. This approach shifts more of the burden to the compiler, which has to break down complex software operations into sequences of these simple RISC instructions. But the payoff is simpler, faster, smaller, and more power-efficient CPU hardware. The IRM architecture, which powers virtually all smartphones and tablets, is the classic example of RISC's success. And now we're seeing RISC make huge strides in laptops and even desktops, most notably with Apple's M-series chips, which demonstrate RISC's potential for high performance combined with remarkable energy efficiency.
So it's really a trade-off. CISC puts complexity in the hardware for potentially simpler software instructions, while RISC simplifies the hardware and relies more on smart compilers.
Fascinating stuff. Wow. We have covered a ton of ground today, from the ALU doing math, the CU directing traffic, registers as workbenches, the whole instruction cycle, performance metrics like clock speed, cores, IPC, the vital role of hash, and now these fundamental ISA philosophies. To try and wrap our heads around all of this, could you perhaps synthesize it? What are the absolute key components and concepts that really define what a modern CPU is and how it performs its magic?
Absolutely. Let's try to boil it down. At its heart, the CPU is truly the brain of the machine, the place where abstract software commands become physical electrical actions. Its fundamental function is defined by that intricate, high-speed interplay of its core triumvirate. The Arithmetic Logic Unit, ALU, performing all the mathematical and logical computations. The Control Unit, CU, acting as the master orchestrator, directing every operation, and the incredibly fast registers serving as its immediate workspace for data. This team works relentlessly through the fetch, decode, execute cycle, often with a store write backstage, bringing software instructions to life billions of times per second. When we talk about its performance, it's crucial to remember it's not just about raw clock speed. It's a complex balance between that clock speed, the number of processing cores it has for parallel execution, and critically, its architectural efficiency, which we measure as instructions per cycle, IPC. Performance truly is clock speed x cores x IPC. And none of this speed would be fully realized without the sophisticated multi-level cache hierarchy, L1, L2, L3. This fast on-chip memory is essential for mitigating the bottleneck caused by slower main memory, relying on the principle of locality. Finally, the CPU's fundamental language, its capabilities, are defined by its instruction set architecture, ISA. This reflects a core design choice predominantly between the hardware complexity of CISC, like by 86, and the hardware simplicity and efficiency of RISC, like ARM. So taken together, the core components working in concert, the relentless instruction cycle, the multifaceted nature of performance, the critical role of cache, and the underlying ISA philosophy. These are the elements that truly define a modern CPU and its role as the engine driving our digital world.
That's a fantastic summary. It really pulls all those complex threads together beautifully. We've certainly moved from just knowing the CPU is the brain to having a much deeper appreciation for the incredible engineering and logic packed inside that tiny chip. Hopefully for you listening, this deep dive has truly helped you become more well-informed about this critical piece of technology. And understanding the CPU and its interaction with memory through cache naturally leads us to our next topic. We hope you'll join us for our next deep dive, where we'll broaden our view slightly to explore the memory hierarchy, from registers to persistent storage. We'll look at the entire journey of data, from the CPU's fastest registers, through caches, main RAM, and all the way out to long-term storage like SSDs and hard drives. Thank you so much for joining us on this deep dive today. Don't forget to subscribe to our channel, Tech AI and Beyond, for more insights into the fascinating world of technology.